Hi, today I want to show you a case study of how Sophus technologies can be used to solve an order assignment problem using a wholesaler in the US as an example. First, we're going to go through some overview of the background of the company, the challenges, and then we're going to talk about the modeling solution, the input data needed, the baseline result, as well as the optimization results in different scenarios. First, let's look at the company itself. Homestyle is a manufacturer and interiors wholesaler based in the US. It supplies various online distribution channels, Amazon being the largest customer. It currently has two DCs in the US, one in the West in Los Angeles, the other one in Louisville in the Mid-East. It's currently shipping to over 100 destinations, which is called FCs. That's Amazon Fulfillment Centers. And the current service level agreement is same-day shipment. That means whenever Amazon makes an order from any of the 108 fulfillment centers, Homestyle will need to pack and dispatch the order on the same day. And that's the problem because we have so many different destinations and so frequent shipments, the average shipment size are very small, which incurs a much larger transportation cost than if you have bigger shipment size. Therefore, the management team is keen to evaluate different opportunities to reduce transportation cost. These are our modeling objectives. The first opportunity is to consolidate the shipment destinations. So instead of shipping to 108 different FCs in our current network, we want to try to consolidate to one FC per state. That would bring down the number of FCs to a total of 31 in the American currently. Another opportunity is to relax the service levels to up to 3 days, which means we can consolidate orders up to 3 days by delaying some of the orders, but combining shipments into larger shipments. We are interested to understand if we did either or both of these things, how much saving can we expect? These savings will come with a cost. Amazon would likely to reduce the price and reduce our margin. But if we can make a bigger saving, this would be a good strategy to pursue. And it's hard to see this by hand, and we need help of a model to do that. Let's talk about the modeling approach. First, we need to use a different type of algorithm to solve this problem. And the Sophus AR team has developed a new algorithm specified to optimize the allocation of shipment orders to lanes and dates. And this will minimize the total supply chain cost. And it can also take into consideration the different constraints, such as the available lanes by period. It can consider the stepwise cost function, which will act as an incentive to combine multiple orders into larger shipments. It can also consider inventory holding cost as a penalty of delaying the different orders. The algorithm can handle millions of records, so the capacity is quite strong. The algorithm can handle millions of records and optimize in a short period of time. The other thing we're going to do in this model is to test multiple what-if questions by using multiple scenarios. So first, on the demand side, we want to be able to test the sensitivity of the saving on the demand forecast. So we have a base case demand, and we can also run the model with the upside demand, which is 5% higher. We can set up multiple demand scenarios if we want. Also, on the network side, as we said earlier, we want to test the current network, which is made up by over 100 FC locations, versus the consolidated destinations, which is 31 FCs in the alternative scenario. On the service side, we want to test the current same-day service versus 3-day shipment window. See how much the model can combine the orders and make transportation savings. Last but not least, we need to think about data input and output processing. It's quite often we spend over 50% of our time on a project just on data gathering, cleaning, and processing. So in this demo, we want to also show you how a technology called Dustro can be used to automate that data processing. Next, let's have a look at the baseline, the key input tables, and the output results. The order assignment algorithm requires fairly simple input, comprises of 5 different tables. The product table needs to show the product we're using in the network. In this case, we don't really care about what is the actual product. We just care about how many pallets. So we can aggregate the product to pallet level, just one product. Site needs to show all the DCs as a source of the shipment and all the FCs, potential FCs in the network. We have a period table that is daily for a year. On the right hand side, you can see we got 2 bigger tables as input. The shipment, which is source, destination, volume by date, and you can also define the shipment window here. So we can choose the latest pickup date and latest shipment date. For shipment lane table, we define the source, destination, and the period and the cost. The cost can be defined in the stepwise fashion. So this shows the economy of scale when you ship larger orders. We can jump into Sophus to have a look at these input tables. This is my Sophus model. Let's go to full screen and have a look at the 5 input tables we populated. So like I said, for the period table, we just need to define the name of each day. In this case, we just use the date format and the start date. And in the end, we have a and period to show when the model should finish. In this case, it's the 1st of January of next year. We have a product table with a single product of pallet. We have size table for the 2 DCs and 108 FC locations. Here we have the type specified as well as the coordinates of latitude and longitude. For shipment lanes, we need to define each possible lane in the network. So from the DCs to FCs of the single product of pallet, we can have this on each single day. So you have opportunity to say on a particular lane, there are certain days that's not available. And we have the step cost here that we can define by different order size. So in this case, anything that's less than 5 pallets will cost $116 each. If it's between 5 and 10 pallets, the unit price comes down to 98, etc. The shipment table is the biggest table we have because it's by order ID. And you can see in here we have the quantity of each order in terms of pallets, and we have the value of that order as well. And this is useful to calculate the profitability of each customer. And we have more on that a bit later. Over to the right, we have these early pickup dates, latest pickup dates, earliest delivery, and latest delivery date. These will define the freedom the solver has to consolidate different orders by period. So those were the input tables Sophus requires to model the order assignment problem. But how do we populate these tables? We can do them manually, but it will be very time consuming and prone to human error. We probably have a different format from the business in terms of the orders and shipments and rate cards. For example, I've got this input file that has the definition of DCs and the FCs with the coordinates. We'll have different products, which we will later aggregate. We also have a rate card that shows the source and destination by number of pallets. So this information needs to be imported, cleaned, and converted into the format we need for the model. And to do that, we use a tool called Dustro by Sophus. This tool is an integrated ETL solution that can link to the various input data, whether it's an Excel file or text file or database, and then it will convert the data into the right format. It can clean the data, it can report any inconsistencies. You can define that workflow to your specification. And then that workflow can be integrated into the Sophus model. So we can see the workflow and run the workflow from the Sophus platform. And this provides a very robust process of data handling because you can always go back and revisit workflow and find out how a particular value got created. And it's also a repeatable process. You can easily swap the data input to the latest one and rerun the whole process with a click of a button. So let's go back to the Sophus model, and you can see in addition to the input tables we've been looking at, there is an option for Dustro. And this will take us to a various workflow I've defined previously. And for this model, we can look at these workflows for the OA demonstration. This particular macro is all about data input and pre-processing the orders. And we got other workflows that processes the periods table, the shipments table, and the transportation rate table. So these processes will import and clean the data, and also importantly export to the Sophus model. Next, let's have a look at the scenarios. As we said earlier, we want to set up scenarios on 3 different business levers, different demand profiles, different network setup, and different service levels. So altogether, that gives us 8 different combinations of different scenarios levers. So we need to set up 8 different scenarios. And setting up scenarios are very easy on Sophus. Let's have a look at this scenario tab. So I've got 8 scenarios set up here, but I could set up new ones easily by duplicating existing ones. So under each scenario, there is a list of scenario items I've set up that I can just drag and drop. So in this scenario, because it's baseline demand, it's using the current DC setup and using one-day service. So all I need to do is in this shipment table, I include the shipments that has one-day service. And there are different records that are already pre-populated using Industrial in the shipment table. So in other scenarios, I could just go to different scenario item where I include the 3-day service level ones. And for the upside demand scenarios, I can just add a new scenario item to multiply the demand quantity by 1.05 to represent the 5% increase. So these scenarios can be set up concurrently and run concurrently using the model run queue. So we can easily select the algorithm we want to run with, and then select the different number of scenarios we want to run. So by clicking run, we can see the model solver is actually running. Let's jump back to the presentation. So when the model finishes running, we can check the output in different output tables. So in the OA algorithm, we have 3 key output tables. There's a summary table that summarizes on the scenario level the total number of orders, total number of pallets, and the cost. And you can drill down to the details in the output shipment lane table that has as the name suggests, lane level output. You can see by source, destination, and date how many orders are consolidated in that scenario, and the total number of pallets and the cost. And if you want to drill another level down, you can go to the output shipment assignment table to see each order ID, which day it was shipped, and whether that's delayed, and the number of pallets and total value of that order. Let's have a look at the model solver. So we can see some scenarios has already completed. And we can explore the output in the output table. We can hide the empty ones. So those are the 3 we just discussed. So we can export that to Excel or use Industrial to do some post-processing. But we can also look at the result from the map and some dashboards. So let's first have a look at the map. Industrial offers this interactive map function for users to create their own map with different layers. You can select different shape, color, and different icons, and you can choose between different scenarios as well. So what I'm showing you here is the current network where we have 2 DCs shipping to the 108 locations. We can also review the output from the dashboard that we create. So I created one that's called result. This customer BI allows you to create bespoke reports in different formats. In this case, I've got a bar chart showing me the high-level comparison of different scenarios. So on the left, I've got 4 sets of scenarios using the base case demand. And on the right-hand side, I've got the upside demand. So looking at the baseline, we can see the total cost is 14.4 billion in the whole year. And that is using 108 FCs using the same day service level. We can also see when we start to relax those constraints. So if we allow 3-day shipment, the model has found a better solution to only use 8.4 million of cost. So that's about 40% reduction. And also if we reduce the number of destinations, we can also see a reduction in the total cost. And finally, if you combine both changes, so that's reduction in number of FCs as well as service level, then you have a compound effect and have some extra savings. So that is about 50% of the original cost. I also have some scattered map here that shows the profitability of the orders. So on the left, I've got my baseline setup where we have 108 FCs. So there are more destinations, more dots on the map. The size of the dot represents the number of pallets for each destination. The color represents how profitable each customer is. So the darker the color, the more profitable. So we can see we got a lot of customers with a high cost over here, and we have a lot of small customers dotted around the country. Notice that the scale is between 2K and 4K pallets. On the right-hand side, we have the consolidated network visualization. We can zoom in a bit. So here we can see that the quantity scale has changed. So the largest dot is representing 36K. So we have much fewer but larger customers after consolidation. And we can also see the profitability has improved because the reduced total cost. And we can also use this view down here to check a particular lane. So I've selected a particular lane here and show the size of the orders by day. So there's 365 lines here. The different color represent different scenarios. So in the baseline where we have the current network with one-day service, we can see we have shipment every day and the shipment are relatively small. And with the 3-day service consolidation in the green color, we can see the model has decided to consolidate shipments to be less frequent but larger shipments. Let's jump back to the presentation for summary of our analysis. First, we compared the network consolidation scenarios. So when we change from the 108 FCs to 31 FCs, we can see there's a reduction of the destination, but also increase the size of the shipment and also improve the profitability. We've compared how the service level has affected the size of the orders and the profitability. And finally, we've observed from the scenario summary comparison dashboard that when we reduce service, we have 42% saving, and when we consolidate FCs, we have 40% of saving. And when we combine the two, we will be expecting 51% of saving. And that is repeated for the baseline demand and the upside demand, and we are seeing the same shape. So at this point, we can be fairly confident in our findings, and the management can take an informed decision about what to do with the next step of negotiation with Amazon. Thanks for your time listening to this case study. If you have any questions, please feel free to reach out. Bye.